Hello. So let's try to go over the important points and applications of the reading assignment, which I sent it yesterday. So, first of all, Laplace transform unit step functions. U of t minus a is 0 if t is less than a, and 1 if t is bigger than or equal to a. So that will be something like so. Before a, we get 0. After a, we get 1. And Laplace transform of u of t minus a equals to e to the minus as over s. I gave you a proof for derivation of this, which is a possible problem for the meter 4. We'll not do it here because I already gave you the proof, and I don't want to waste additional time here. So you got unit step function. Then connect to this one rectangles, so rectangular signals. Rectangular signals. So I do not have a rectangular signal by rectangle from A to B and altitude h of t is again 0 if t is less than a. H if t is bigger than or equal to a and smaller than b. And then again 0 if t is bigger than or equal to b. And the picture will be this one. Prior to a is 0. This would be a, this would be b, for example. Prior to a is 0. Between a and b, bigger than or equal to a is more than b. So we have this kind of line, close here, open here, is h. And after b, if t is bigger than or equal to b, is 0 again. So rectangular signal from here is 0, h, again 0. Okay, so the Laplace transform of this one is directly Laplace transform is h times e to the minus as minus e to the minus bs over s. Because the rectangular signal can be expressed as h times the difference of two unit step functions. So note that RAD h of t is h times u of t minus a minus u of t minus b. So that's how we get the rectangular signal in terms of unit step functions. So this rectangular signal in terms of unit step functions. Rectangular signal like this kind of rectangle between A and B and altitude h is RABH of t is h times u of t minus c minus u of t minus b. And clearly the transform is this one. So h times Laplace of u of t minus a is this one, e to the minus a over s, minus the Laplace of u of t minus b is this one, minus e to the minus bs over s. This kind of shows that why the Laplace transform of the rectangular signal is what we claim it is. Okay. Another important topic from the latest reading assignment: delays. So actually, one discuss about the role of unit step function in delays, quote unquote delays. What does it mean? Let's assume that we have a function f of t, which let's call it, picture it as f of t, transforms in some Laplace transform big f of s. Let's delay the application of f of t. So keep the same graph, but make it start later. So let's delay the application of f of t. So delay f of t with a. So basically, we have a right shift of f of t, but towards the left, we put 0. So 0 until a, so nothing here. But after a, put again the signal, the same shape. So delay this signal until a. So this delay signal is, the formula for this one is u of t minus a, f of t minus a. So f of t minus a is the right shift of the function f of t. So why do we have to put u of t minus a? Because imagine that this graph has also a left tail, something like this. If we only shift it, we'll get a left tail like this. By multiplying by u of t minus a, we guarantee that the left tail of this signal is 0. So the signal actually starts to be applied at a with no left action. Okay, so the delay of a signal is u of t minus a, f of t minus a. So very important formula for the Laplace transform. Okay, let's try to discuss about the Laplace transform of delay. And let's assume that f of t starts from 0. Let's assume that f of t is a Laplace transform of big f of s. This is small f of t transformed into big f of s. Let's apply the delay. Delay with a. So this will be delay the signal until a, otherwise you get the same signal. And this one will be u of t minus a, f of t minus a. That's the formula for the delay signal. Now, the main theorem here is the Laplace transform of delay is e to the minus as big f of s. So if the original signal transformed into big f of s, the delay signal, delay with a, transforms e to the minus as f of s. So the Laplace transform of u of t minus a, f of t minus a, equals to e to the minus as big f of s. In particular, how to find the inverse transform. L inverse of e to the minus as big f of s. What do you do it? How to do this? Big f of s, transform it back into small f of t. So that's what we do in our minds. Transform this one with small f of t, and then delay it. So this will be u of t minus a, f of t minus a. Good. Now, this being said, let's do an application. Exercise. Again, it's a part of similar to one in the latest homework. Exercise. Find the inverse transform of e to the minus 2s and 1 over s to the power 1. So remember what I told you before. So first of all, take this function and do the inverse transform. Let's try to do some work to find the inverse transform of this one. So let me recall that Laplace transform, which is the closest to 1 over s to the power 5, is t to the power 4. Laplace transform of t to the power 4 is 4 factorial over s to the power 4 plus 1 is 5. So the Laplace transform of t to the power 4 is 24 over s to the power 5. Okay, and then by linearity, Laplace transform of t to the power 4 over 24 equals to 1 over s to the power 5. So the inverse transform of 1 over s to the power 5 equals to t to the power 4 over 24. Okay, so exactly what we put here. To invert 1 over s to the power 5 is t to the power 4 over 24. Okay, so let's try to, that's the work. Keep the fruit of the work, there is the work. So we put here t to the power 4 over 24. Then let's apply the delay theorem. So to find the area inverse of e to the minus as bk of s, invert this one, we'll get t to the power 4 over 24, we'll get u of t minus 2 times t minus 2 to the power 4 over 24. So what will be the graph? Until 2 is 0 because of u of t minus 2. After 2 is t minus 2 to the power 4 over 24. It's like a thing like this. That's the formula for this variant. So that's the delay of t to the power 4 over 24, delay with 2. 0 until 2, t minus 2 to the power 4 over 24 after 2. Okay, so that's one application of this formula. And let's finish with the initial value problem. Let's see, we got this one. Let's solve the exercise 2. Solve the IVP. The IVP is x second plus x. It's an oscillator. X second plus x equals a rectangular signal between 2 pi and 3 pi. Rectangle from 2 pi and 3 pi with height 4 of t. So basically, we have a signal which is between 2 pi and 3 pi is 4. Pretty much like a raw description. A rectangular signal between 2 pi and 3 pi. Of course, there are more sharper picture with the open circles, field circles, and so on. But basically, that's it. So rectangular signal between 2 pi and 3 pi with height 4. So we got x second plus x is this rectangular signal. And initial conditions, x of 0 is 0. And x prime of 0 equals to 1. That's an IVP. Let's find the solution of this IVP, and then the amplitude of the resulting oscillation after 3 pi. So on find amplitude after 3 pi. Okay, so let's solve this problem. Okay, so let's try to apply the Laplace transform. Let's say declare our intent to use the Laplace transform. So small x of t goes into big X of s. Then x prime goes into, because x of 0 is 0, is sx minus 0, just sx. And x second goes into s squared x multiplied by s and subtract the next initial condition of 0. So s squared x minus 1. And finally, the rectangle r from 2 pi, 3 pi, with height 4 of t transforms into 4 times e to the minus 3s, e to the minus 2 pi s minus e to the power minus 3 pi s over s. Because the rectangular signal is a difference, is 4 times the difference of unit step function u of t minus 2 pi minus unit step function u of t minus 3 pi. Okay, so this, with all those transformations, let's try to convert everything to S space. So convert to S. S space. So we get x second is S squared x minus 1 plus big X equals 4. Okay, let's get a transform of S squared x minus 1 plus big X equals to 4 times e to the minus 2 pi S minus e to the minus 3 pi S over S. Okay, so let's see. Now let's pull keep all the x's on the left, non-x's to the right. So let's see. X times S squared plus 1 equals to 1. Let's simplify this one. 1 plus e to the power minus 2 pi S times 4, right? Times. So we have to divide by 4 e to the minus 2 pi S over S. So x times S squared plus 1, but this one kept on the left, move minus 1 from left to right. So that's why I got 1 plus 4 e to the minus 2 pi S over S minus 4 e to the power minus 3 pi S over S. So basically, we just use the formula A minus B over C is A over C minus B over C. We just expanded this fraction here. Now divide by S squared plus 1. So X, capital X equals to 1 over S squared plus 1 plus 4 e to the minus 2 pi S times 1 over S times S squared plus 1. That's what we get if we divide by S squared plus 1 this unit. So 4 e to the minus 2 pi S times 1 over S from here and S squared plus 1 if we divide by S squared plus 1 minus 4 e to the minus 3 pi S times again 1 over S times S squared plus 1. Okay, so this is capital X. Let's try to work a little bit more on this. Okay, we don't need anything but what was before because that's the most updated information. Okay, so no, we don't need this one. We are here. So now on the side, we have to do one partial fractions. To use partial fractions to write 1 over S times S squared plus 1 as a sum of partial fractions. So partial fractions for 1 over S times S squared plus 1. This will be A over S plus BS plus C over S squared plus 1. Let's try to bring the common denominator. 1 equals to A times S squared plus 1 plus S times BS plus C. Or in other words, 1 equals to AS squared plus A plus BS squared plus CS. Let's start to equalize. S squared. A plus B equals to no A squared here is 0. S to the power 1, let's equalize. C equals to 0. And S to the power 0, the free coefficient. A equals to 1. A equals to 1, C equals to 0, and B equals to minus 1. So A equals to 1, we'll get 1 over S, C is 0, B is minus 1. So we'll get 1 over S as a result, 1 over S minus S over S squared plus 1. That's the result of the partial fractions. 1 over S times S squared plus 1 is 1 over S minus S over S squared plus 1. Let's write down the work and erase the, let's write down the fruit of the work and erase the work. So this will be 1 over S times S squared plus 1 is 1 over s minus s over s squared plus 1. Okay, so with this in mind, let's write again the capital X. Capital X equals to 1 over s squared plus 1 plus 4 e to the power minus 2 pi s times 1 over s times s squared plus 1. We just did the work before. Now let's use the fruit of the work. 1 over s minus s over s squared plus 1. Okay, we got this one. No, minus 4 e to the power minus 3 pi s times again 1 over s times s squared plus 1, which is 1 over s minus s over s squared plus 1. So you got exactly this. That's the most updated version of capital X. We don't need the older version. Now let's move on from here. So that's basically the solution of differential equation encoded. So let's see. Let's do the transform. Remember, 4 is a, don't bother about this 4 or minus 4 here because it's just linearity. This is important. In a minus as before a big F of s. Transform like we discussed in the previous problem. This one transform this one. 1 over s transforms back into 1. S over s squared plus 1 transforms back into cos t. So if we want to transform all this difference, 1 over s minus s over s squared plus 1 will be transformed in 1 minus cos t. Same here. This whole difference, 1 over s minus s over s squared plus 1, transforms back into 1 minus cos t. Right, but let's write down small x of t now. Transform back 1 over s squared plus 1 is sine t, plus 4. We get e to the minus 2 pi as before. So we have to insert u of t minus 2 pi. It's a shift, u of t minus 2 pi. And this function calculated at t minus 2 pi. So what do you write here? 1 minus cosine of quantity, instead of t, put t minus 2 pi. Close. Minus 4. Again, we have a delay, u of t minus 3 pi. And this function, 1 minus cos t, calculated at t minus 3 pi. So times parentheses 1 minus cosine of quantity t minus 3 pi. Close. Okay, that's the most updated version for small x of t. Okay. Now let's try to gain more space. So what we get here? Use some trick. So some trick formula. Cosine of t minus 2 pi. Because of the periodicity of the function, cosine is cosine of t. The cosine is periodic function with a period 2 pi. Okay, so what about cosine of t minus 3 pi? Equals to, use the trick formula. Cos a minus b is cos a cos b plus sine a sine b. So cos t cos 3 pi plus sine t sine 3 pi. Sine 3 pi is 0, which makes sine t sine 3 pi is 0. Cos 3 pi is minus 1, and this will be minus cos t. So cosine of t minus 3 pi is minus cos t. So 1 minus cos t is 1 plus cos t. So, okay, so let's see. This is 1 minus cos t. And 1 minus cosine of t minus 3 pi is 1 plus cos t. So let's write again. Small x of t equals to sine t as before plus 4 u of t minus 2 pi times 1 minus cos t minus 4 u of t minus 3 pi times 1 plus cos t. Now, the final result I want you to express in the form of a chart. So chart is a real number line divided. What are the critical points at which the regime of the oscillation changes? 2 pi and a 3 pi, right? So let's see. The chart will be again, if I tell you the test, do the chart as shown in class, you do this. So let's start from 0, then we get a sum moment 2 pi here and 3 pi here. Let's put 2 pi a little bit earlier so that I don't want to occupy too many space with simple things. So 2 pi here and 3 pi a little bit later. Okay, I ignore the scaling here. So what is what happened is what? Prior to 2 pi, so this is a unit step function. The jump happens at 2 pi. Here is a jump which happens from a 3 pi from 0 to 1. Before 2 pi, no jump happened yet. So before 2 pi, so in this area, it's just this one, because no subsequent jump happened yet. So it's f sine t. What happens between 2 pi and 3 pi? This jump happened. The second one did not happen yet. So this becomes 1 here. So sine t plus 4 minus 4 cos t. So sine t from before plus 4. This is 1 at this moment, after 2 pi, but prior to 3 pi. After 2 pi, the unit step function jumps from 0 to 1. So after 2 pi, we get 4 times 1 times 1 minus cos t, which is 4 minus 4 cos t. After 3 pi, what happens? Is what we got before. So let's write what we got before. Sine t plus 4 minus 4 cos t plus the new Kirchhoff block. Now the second jump happened. Okay, so minus 4, because a minus in front. Minus, this becomes 1 as well, 1. Minus 4, right? Minus 4 here. Minus 4 cos t again. So minus 4 cos t. So which is what? Let's try to simplify this. After 3 pi, after t equals to 3 pi, we get sine t. Okay, plus 4 minus 4, they cancel out. Sine t, so x of t sine t minus 8 cos t. X of t equals to, so it was here. No reason, but x of t equals to sine t minus 8. So that's the exact formula for the oscillation after 3 pi. And then the second question is amplitude after 3 pi. Amplitude for after 3 pi. This one, amplitude for after 3 pi is square root of the sum of the square root of coefficients of sinus and cosine. It's square root of 1 squared plus 8 squared, square root of 65. And that's the answer of the problem. Okay, so we are entering this new territory with non-continuous discontinuous function with jumps and delays and stuff like this. So until you get the hang of it, so take a look at the reading assignment and the set of problems I sent connected with this area. Okay, so I'll see you tomorrow then.